Got a linear transformation problem, a couple actually, to go over with y'all, just to give you a feel for what we might be trying to do here. So we've got, I'll look at the one on the left first here. We're wanting to try to determine a basis for the range and a basis for the kernel. Okay, so we want to get a basis for the range and a basis for the kernel. So the first thing we want to do is we want to get the matrix, the standard matrix for the transformation. And so how we can do that, this is sort of the default or the by the definition way here, is to find out, well, where do the basis elements get mapped? So the standard basis for R2 is 1, 0 and 0, 1. So we'll find out, well, where does 1, 0 get mapped? Well, here x is 1 and y is 0. So this is 2 times x plus y. So that's 2 times 1 plus 0. Okay, well, that's 2. I can work out that arithmetic there. And then the next component is just x. All right, well, that was 1. And then the next component is x minus y. That's 1 minus 0. Okay, well, that's just 1. So we see that the vector 1, 0 gets mapped to 2, 1, 1. All right. And then we have 0, 1. Where does that get mapped? And again, those two vectors, 1, 0 and 0, 1, you might be wondering, where is he getting those? Those are the standard basis for R2. R2 is the domain of this transformation. Okay, so we see that we got x is 0, y is 1. So in 2x plus y, that'd be 2 times 0 plus 1, which is 1. And then x is 0, again, because for whatever reason, in the second component of the linear transformation, it's just x. And then we have x minus y. Well, that's 0 minus 1, so that's a negative 1. So those two vectors become the columns of the standard matrix. So we have 2, 1, 1, and 1, 0, negative 1. That is our standard matrix. And you might look at that and say, okay, well, why do I need that? Well, what that is, what it alludes to is the fact that any linear transformation we can write as matrix multiplication. So if I have a vector xy, a column vector xy, and I multiply it on the right side of A, well, the result is going to be, 2x plus y, x, and x minus y, the exact output of the linear transformation. And so when I want to find a basis for the range, or if I want to know what the range is, well, then I will look at the basis of the column space of this matrix. So again, we're sort of reaching back to the previous unit, and so we're going to get this matrix into row echelon form. So we'll get this thing in row echelon form, and I am going to let y'all work out how to do that by hand, or even you can throw that into the calculator to do that. But how this is going to work out is rather nicely. We're going to get 1, 0, 0, 1, and 0, 0 as the rows. So now thinking about how we get a basis for the column space, again, we look for the leading ones. Well, we have 2 leading ones, 1 in each column. It worked out rather nicely there. So the two columns of A are the basis for the column space, and that's also the basis for the range of of R3. Well, the basis of the range of this transformation. It sits in R3, but it isn't all of R3 though. Okay, so the basis for the range okay, so we'll have uh it turns out it's just going to be precisely the two output vectors from plugging in the standard basis to the transformation. It isn't always going to be that way. It just happened to work out that way here. All right. So that is the basis for the range. If you wanted to write what the range was, well, you would put the word span in front of those braces. The span of those two vectors is, in fact, the range, because again, it's the basis for the range. But also note that those are just two vectors, not three. So this transformation doesn't span R3. It doesn't span the entire codomain. And so we would say that the linear transformation T is not an onto transformation. Okay, onto means that everything in the codomain can be reached by an image of the transformation, or basically everything in the codomain is an image of the transformation. So, yeah. So then the other question was, what is a basis for the kernel? And that is associated with the null space of the matrix. Well, if we go back to the row echelon form, here that's actually reduced row echelon form, we know the null space is we set the matrix, basically trying to solve the equation AX equals 0. So if I throw zeros on the other side there, that's basically telling me that, okay, the first variable is 0 and the second variable is 0. X and Y both have to be 0 here. Because again, that's what this first row is telling me. X, 1x plus 0y equals 0. X equals 0. 0x plus 1y equals 0. Oh, y equals 0. And of course, the bottom row, 0x plus 0y equals 0. So 0 equals 0. Okay, I knew that before I started. But anyway, so the basis for the kernel, well, basis of the kernel essentially is just the kernel. It is the 0 vector. Because all we got was just one unique solution, that X has to be 0 and Y has to be 0. Remember that the kernel is the set of all vectors in the domain that get mapped to the 0 vector in the codomain. And it turns out that here, the only thing that gets mapped to the 0 vector of the codomain is going to be the 0 vector in the domain. So whenever this happens, whenever the kernel comes out to be just the 0 vector, we say that the transformation is 1-to-1. Remember that a function, a transformation or a function is such that every input has exactly one output. A 1-to-1 function works the opposite way as well. Every output has exactly one input. And so that's going to happen when the basis for the kernel is the zero vector. So this linear transformation, we have a basis for the range, so we know what the range is. We have a basis for the kernel, we know what the kernel is. And we know the transformation is not one-to-one, but it is onto. I said that backwards. It is one-to-one, but it is not onto. Okay, so strike that, reverse it. Because the kernel is the zero vector, it is a one-to-one transformation. Because the basis for the range is not the same dimension of the codomain, the transformation is not onto. Okay, let's look at the problem on the right, the one I've got in blue there. Okay, so this is a little bit different because it's a transformation from R3 to R2. And so we've got x, y, z gets mapped to 4x minus z, comma, 2x minus 2z. Okay, that's a bit interesting there. So we'll proceed as we did before. We will see where does the standard basis get mapped. So 1, 0, 0. We see that's going to get mapped to 4, 2. And then we have 0, 1, 0. Okay. Well, note that the output of the linear transformation doesn't involve y at all. X and z are both 0, so we get 0, 0. Okay. And then if we look at the mapping of 0, 0, 1, okay, here z is 1, everything else is 0. So there's going to be -4 and -2. Okay. So this is going to be, these are going to be the columns of A. So we get 4, 2 as the first column, and then 0, 0 as the second column, and then -4, -2 as the third column. All right, so that is the standard matrix for this linear transformation. Again, I'll get this into row echelon form, and actually this is probably going to be reduced row echelon form again, because this is kind of simple. Okay. And again, do it by hand or throw it into the calculator. So this is, oopsie. So this is the, yeah, again, the row echelon form for our standard matrix. So we only have one leading one. It's just this first column here. That -1 over there, number 1, it's a -1. Number 2, it's not leading. So we only have one leading one. So basically, the basis for the range is just the vector 4, 2. And, I could factor a 2 out and call that 2, 1 even. Okay. But if we want to just, stick to what we've got here, this does work. All right. So the basis for the range, or a basis for the range, is just a vector 4, 2. Okay, so yet again, we've come up one dimension short for being onto. Okay, it does not map to all of R2, just a one-dimensional subset, or one-dimensional subspace rather, of R2. And then what gets mapped, what is the kernel? What gets mapped to the zero vector? Well, if we toss a couple of zeros out here and say, all right, well, what is this telling us here? Well, here I've got 1x, and this is minus z equals 0. Okay, well then x and z have to be equal, and y could be anything. Doesn't matter. So we can have a parameter for y and a parameter for z, and we can get that x would have to be equal to t, z would equal t, but y would equal s. And so if we sort of line that up here real quick, x, y, and z. Again, this is similar to the idea of a uh, basis for a null space. Okay, so again, this x and z are both t. Yeah, so we have like basically one t and no s. And here I have one s but no t. So for the kernel, again, the basis for the kernel, okay. Again, thinking about the t's, that would be 1, 0, and 1. And for the s, it'd be 0, 1, 0. Okay, so that's a basis for the kernel. So in other words, the span of those two vectors is the kernel. So the kernel is two-dimensional. So in other words, this linear transformation is neither one-to-one, nor is it onto. Okay, so yeah. All right. So I was just making sure, double checking, make sure everything looks right. Okay, so that's basically it. So I'll give another problem in another video where we've got polynomials instead of R2 and R3. We might have like P1 maybe. And so we'll see you next time.